Everybody, can you hear me? Yeah. Okay, welcome back, everybody. I would like to introduce our keynote speaker today. Valerie Taylor is the director of the Mathematics and Computer Science Division at Argonne National Lab, and I'm proud to call her my boss. Uh, Valerie's earlier career spans a stint as a faculty member at Northwestern, from which she moved to being a faculty member at Texas A&M. So, like Chameleon, her career spans Chicago and Texas. So it's a great connection to the project. And then Valerie is known for her research on performance analysis, HPC, and more recently, power evaluation. And the most power efficiency. And most important thing is she's a Chameleon user. So she will tell you about fabulous research in the area of AI on Chameleon. Take it away, Valerie.
Thank you, Kate. And I think more as a colleague than. Okay, so is my microphone on? Are we good? Okay, so I just want to say I really enjoyed the panel on education. So that was so engaging. And I'm going to do a bit of a switch to talk about some research that we've been doing with Chameleon. And because we're doing work with energy efficiency, that's where Chameleon was really beneficial. And I think this came up during one of the presentations where you were looking at power and you had power on CPUs, but when you get to power on GPUs, you need to have the drivers for those specific GPUs. And when you go on a production system and say, I need to install these drivers, you either put in a ticket in which you wait, or if you go, I can do the installation, then they look at you and know you're joking. Like, you've got to be joking, please. So this was great. So I just want to tell you about our research, but I'll talk a little bit too about what we did with Chameleon. So first, in terms of this work, I want to acknowledge the team. That includes researchers at Argonne and also UIC, and that's University of Illinois at Chicago. So it's a great group. So with Chameleon, it provided the bare metal platform for the experiments. We were able to get the time we needed, which was great. We were able to get the dedicated access that we need to actually do the measurements and have some confidence in the measurements. And we did a large number of measurements. So just to go a little bit more into detail now, to frame the work that we're doing, and that is looking at large language models for software generation, but then I'll go into detail about the energy efficiency. But if we put this in context, I think everybody's been hearing about the use of AI for a computational assistant. And that is when you look at that use of AI for a computational assistant, you'll start off with an open problem. You may do a mathematical formulation, do some maybe numerical formulation, and then from there you want to go to an efficient algorithm, have the parallel implementation, do some type of simulation, have the analysis, and have the feedback. You may also have some experimental work that comes in, but you have this aspect of looking at how AI can be used in terms of this whole cycle, in terms of what you're doing for computing and understanding computational science. So when we look at this, the part that we focus on has to do with efficient algorithms and also the parallel implementation. So when we look at also the reason, and I think everybody recognizes this, the reason that LLMs work so well with code generation, and that is you have different syntactic and semantic rules. So it's very much rules-based when you look at programming languages. Also, there's an abundance of open source repositories that's available for different code segments, some more than others, such as Python. You can find an abundance of code repositories. but maybe not so much for Julia. Then you can also, oftentimes, when you're looking at code, you have well-defined tasks that you want done, which lends itself very well. Then you can have code that's modular. So you can have it work on different pieces of the code and then build up to something more complex. And it's important for the scientific process. So when we look at the full scope around large language models with code generation, there's many different aspects. There's correctness and reliability. There's also around prompt engineering, because a lot depends on how you prompt. Then there's also security and safety, performance and efficiency. There's maintainability and readability, license and attribution. I want to note when I talk about correctness and reliability, there's also the aspect of reproducibility that comes in. The part that I'm going to focus on is a little bit on correctness. There's a lot more that's needed in that space, but also a lot more that I'll focus on performance and efficiency. But I just want to note the full scope of things to look at with scientific code development. So for my talk, I'll talk a little bit about our early work that had to do with using large language models for code translation. So that's when we started about 2 years ago. And so that was very interesting. Then we extended to energy efficiency, and that's been where Chameleon really played an important aspect for the energy efficiency, and then talk a little bit about future work. So with Lassie, when we started off with the project, we were having fun using LLMs. And so we were joking around, it's like teaching an old dog new tricks, okay? And so someone asked me, who are the old dogs? And I go, we are, okay? And I included that person in that group, we are. So hence our name Lassie, which is LLM-based automated self-correcting pipeline for generating parallel scientific codes. So how many people are aware of the show Lassie? Okay. So see, our Lassie has glasses, okay. That adds the intelligence. Because Lassie was this, Lassie was this dog that anytime you were in trouble, it didn't matter if you were 10 miles away, 20 miles away, somebody would go, Lassie! And Lassie would run and suddenly appear to help you out of a well or whatever. So that's the show. Okay. So we try to have a little bit of fun with it. So here, in talking about using it for translating code, that's where I'm going to talk about. We actually ended up with a pipeline, and that's what we're talking about, this self-correcting pipeline, where we did a lot of self-prompting. We get feedback, because you can have compiler errors, you can have execution errors, and so we want to have that feedback. So I'm just going to show, we did some work of evaluating translation between OpenMP and CUDA. And we did bidirectional, but I'll just show a little bit of the results. And we did 10 code segments, and at that time we used some early, about 4 large language models. But now, and I'll show what happened when we used some large language models that are more current. So we'll talk about that in a moment. But in terms of the prompting strategy, what we did, so we start off, and it's independent of any large language model. So you can plug in any given model that you want. And so we'll start off with a prompt, as you usually do, like you're a professional coding assistant that specializes in translation, and we give that. And so what we start off doing is first, with respect to the source code and the context, so that's where, because we're doing the translation with CUDA and OpenMP, We used some material from the reference guides, depending on the translation. We also, at that time, imagine 2 years ago, I know a lot has changed, but we took the minimum of the context window size, which was about 16K tokens, and we also had the original code. So we had the source code and that curated content, and we would feed that to the LLM to generate a summary for us. Then we also provided a description of the code that we were using, and that provided our context. So that way we had LLM that was familiar with the code, having gone through the code base to say what's the functionality. So then here we're using all of that information to generate our prompt, which then goes through, generates the code. We may compile the code. If it fails, we do a correction prompt back to say, here's the error, so you should be able to fix it. And we had a number, like if it didn't fix it after 10 tries, it would stop. But we actually had self-correcting, which usually about 1 or 2 attempts, so it wasn't where we ever had to get to that point. We also did execution. And here, because we were working with a benchmark suite, we looked primarily at the output of the benchmark to actually see, because we were just doing code translation. But when we get to the energy efficiency, I'll talk a little bit more about what's needed there. So we would generate again, and then let's say now it executes, so we can save the code and also the metadata. And by metadata, we're looking at how many correction loops we actually had and things like that. So just to go over this real quick, so here's our benchmark suite where we use HeckBench that came out from, this is with Jeff Vedder's group at Oak Ridge, and he published a paper about the benchmark suite, I think in 2023. It has about 350 different benchmarks from various sources. The good thing about this benchmark suite is that it has the benchmarks in many different languages. So it'll have C++, OpenMP, CUDA. So you have all these different versions of the code that you can do the comparison with. So because we were doing translation, this was a nice benchmark suite to work with. And then we just used here NVIDIA A100, we were just collecting execution time. So that was pretty straightforward. So here's the different LLMs that we used. So you probably will laugh, oh, that was back, 2 years ago, Cold Stroll and Wizard Coder. And that's when we were using GPT-4. So. But just want to give some results because we extend this, but here, that is when we looked at the codes, and when we looked at this, we had 80% of the codes we were able to translate from OpenMP to CUDA, 85% from CUDA to OpenMP. When we looked at runtime, 78% of the codes performed well. That was within 10% or even better than what we had in the benchmark suite. And 62% performed within 10% or better from going to CUDA to OpenMP. So this table, which you probably can't read very well, but it's just to say you're starting to see some NAs, and the NAs are where we were unable to get the translation. But now, when you have reasoning models, so reasoning models, you just see a really big difference with reasoning models. So the reasoning models where we started with GPT-01 preview, here, the interesting thing is that we were able to do the translation for all 100%, and it was only in one case that it had to go and do one self-correcting loop, okay? So reasoning models now, where you're taking some time to reason, and it was the chain of thought, reasoning, and you're giving that context, it does much better in terms of the code translation. And we also wanted to explore what happened when we actually had context versus no context. So we were trying to explore different avenues. And this just gives you some of that data, but the context was 45% better improvement in terms of being able to have the translation. But you can see with the O1 preview, which is the one reasoning model, we were able to get 100%, but both ways with the translation. And so now reasoning models are common in most LLMs, and so you're seeing you can get really high rates in terms of the code translations. However, so now the next question that came up, okay, we gave us a chance to play around with the code translation, and this is where we wanted to extend to energy efficient. And that is recognizing that energy, if you look at it, is the capacity to do work. So energy, you look at it on average, you can look at it in terms of your average power times the execution time of your application. And so this gives you an opportunity to look at trade-offs between execution time and also power. But it's influenced by the hardware, the software, also the workload and system, but especially the hardware, which means, like for example, in current hardware, where you can have low precision 4-bit, 8-bit operations, that results in significant energy savings versus doing 32-bit or even 16-bit operations. And so what we wanted to do, and also in different architectures, you'll have a different memory subsystem. So how do you take advantage of that memory subsystem? So it's not where you can just say what I have for an A100 will be the same as an MI 100 or an AMD versus a GPU. So you need to take into account some aspects about those systems. And so that's where looking at energy efficiency, when you look at large-scale systems, and you hear about this now quite a bit with data centers, you look at environmental stability, sustainability, not stability, but sustainability. Also with large-scale systems, such as exascale systems, it's the cost in terms of providing that power. Oftentimes, you have to do restructuring of a current facility to accommodate the power requirements. So that's important. Then you're looking at also, it becomes also an innovation driver to look at the energy efficiency, because now you can, within a given budget, you can do more work as well. So here, now it's a little more complicated in terms of the pipeline, and I'll go over this. But so what we're doing now is that our context, in addition to looking at the code, we're also looking at the target hardware. But it's not just taking the target hardware without doing some execution on that target hardware. Because you want to know if the refactoring of the code actually resulted in better energy efficiency. And so we thought estimates, while they're okay, it doesn't give you the best insight because there's a lot more that goes on in a system than what we parameterize in terms of models. And so here, that's where we're doing some measurements. So when we look at LASI EE, we'll start off with stage 0, where we're doing some code profiling. So we'll do the power profile of the code that we're starting with as our stage 0. Then we'll go through and just note here where we want as our baseline, we're just giving an LLM and say, make it more power efficient or energy efficient for this target architecture. We're giving it context, but we're just doing a zero shot and have the efficiency that results from what we call baseline code refactoring, okay? And that's very similar to the LASSI original framework, except here we're looking at energy efficiency, and because we can have significant changes to the code, we actually have an agent that's doing a lot more than just checking the output. The agent is also checking the functionality, that you have the same functionality of the original code that you have with this code. So it's doing a lot more checking in terms of that new code because it's changed a lot more, okay? Here, stage 2, so now we have stage 1, it gives us that baseline. Stage 2, this is where we actually do a lot in terms of looking at the context for the target platform and also doing a planning. So here, with the context, what we'll do is to prompt the LLM to say, give us a refactoring plan, okay, for this target architecture where you do have some initial power profiles, because you have the power profile from the code, profiling from stage 0, and also from stage 1. And you can use that to help you to get information about the target architecture such that you get a refactoring plan. Okay. Next, stage 3. So this is where we're going to iterate through the refactoring plan, because it doesn't do all the refactoring at one time. A lot of times you'll have a prioritized refactoring. And so we're going through, and we'll go through our refactoring plan and do piece by piece. But what we're doing here is we're iterating through the process to identify if we did, when we refactor the code, did it give us a better energy profile? So we're doing measurements at this point as well. So we're constantly doing measurements. So we need an infrastructure where we can reserve, schedule, and upload our drivers and do these measurements. Okay. So Chameleon is right there. Okay. And then we can terminate. Let me just add with stage 3, what we often do here is to look at some number of iterations. So just to go through this, let me just mention this back. We go through 10 iterations, okay? So if we have 5 iterations where it doesn't have a good improvement in energy efficiency, we stop. Because you kind of go, okay, after 5 iterations, let's not keep going. However, you may go 2 iterations and then restart. And then you have the third one, you end up with better energy efficiency. So another condition for stopping is to say maximum of 10 iterations, okay? Because we don't want it to keep going. So here's an example of where we're taking a Jacobi. And so here, and this is using Chameleon, where we're using the NVIDIA A100. It's an 80 gigabyte. So we're starting off with the code profile, and it's about 7.9 seconds, and we have about 1.2 kilojoules in terms of the energy. And we do take measurements so that we're taking off idle power. So now, the next stage, where we're doing stage 1, where we go through here, and this is where we used a reasoning model, we use GPT-03 Mini. So in this case, what we did was we said, now generate more energy efficient code, and we wanted to make certain the LLM as a judge agent, that becomes important because it's changing the code. So now we ended up with about a 30% energy reduction. Okay, kind of go, oh, that's pretty good. So next, we generate, this is where we start to generate a refactoring schedule. And so here, that's where first to generate these refactoring schedule is first going through, and it uses the programming guide, hardware configuration, and the source code, but it first goes through and identifies code inefficiencies within the code, and then it'll give you a refactoring plan. Okay. So now when we go through that stage 3, where we're doing this iterative self-prompting, because now we have this refactoring plan, so here we can see a better reduction within the code. And so this is where we're going through, and what we can see in terms of some of the refactoring that was done was it did pinning to host memory, it did cache preference of working with your memory hierarchy, it did also a dedicated CUDA stream for asynchronous error copy, it also did a lot of more asynchronous memory operations. So it's going through and looking at where you have code inefficiencies and generating a refactoring plan and actually refactoring the code. So here, and this is what we found in terms of, just to give an overall example of where we're taking the LASSI EE and going through that stage 3. So here, in terms of the LLM comparison, because what we do once we have the code that works the best in terms of best energy efficiency, we also ask the LLM to give us a difference, summarize the difference in the code, because it's gone through and it may have done several refactorings. And so here, this is where we find where it did fuse iterations in a single kernel, eliminated swapping, improved memory transfers, and it did a lot of asynchronous operations, so reducing the synchronization, and it reduced the error computation overhead. Because in Jacobi, you're iterating to get to solve AX equals B, and you're iterating until you get to a solution, because you're not doing a direct solution, it's an iterative solution, until you get to within a given error. So that's what that error is corresponding to. So this gives you some idea of the refactored code, but it ended up with about a 46% reduction in energy. So we were really happy.
I'm sorry, maybe you've mentioned this
Oh, no.
before, but how do you make sure that what you refactor is actually correct? Because these models, of course, can remove code and then becomes energy efficient.
I know, it can just do a print error.
Or something a little bit more subtle. It looks like the same code, but it's dropping some corner case or something.
Right, so that's where we do a lot more in terms of LLM. We have an agent that's going in to look at and say, what's the functionality of the code, in addition to looking at a number of test cases to actually look if you're getting similar output. And that's, we recognize that it's not going to be exactly the same. There could be, we have error bars that we allow. Yes.
So since you are not trying to achieve bitwise identical, and then you say like there are some error bars, so how do you determine the error bars?
So here we actually looked at, we said we just wanted like 1% error. We actually set it. Yes. Oh, are we okay?
Yeah.
We also do see some configuration changes. So the type of thing where you call refactoring could involve also configuration changes across the stack, because
Can involve, what was it?
configuration changes, like
Across the stack?
yeah, like at line 2, I do see that you set the cache config for
Right.
CUDA.
Right, so we can do configurations that can be specified in the code, yes. If it's configurations outside of the code, we don't. Yes. So if there's a system, a configuration that requires that it be done before you start your code that's not programmable, then we
Everything
don't.
that you can program it, right?
Right.
Thank you.
So here, and I'm just going to give some initial results. So here, and this is where we use, with the Chameleon, going into a little more detail, we use the testbed nodes at UC and TAC with AMD EPYC, and then we evaluated the applications on 2 different GPU platforms. So we used the NVIDIA A100 and the AMD MI100. And here is where being able to install the NVIDIA driver version, 56.35.05, it gives us the ability to actually go in and do the power measurements. And the same with the AMD MI100. Again, that gave us the ability to do power measurements. So we don't have that on other systems. We've asked, but we thank you, Chameleon. So I just have to say, this enabled this research. So when we did the energy efficiency, we went to 22 benchmarks. We wanted to have a larger suite. The first one of the code translation, it gave us an entry into working with LLMs and working with code, but now we want it to be a lot more detailed. And so we use some also mini apps as well. So here's some of the results. Don't worry about trying to read it. Okay. But I'm just going to tell you what we have in there. So we give results from both GPUs. Here's the energy savings. We can get also the power savings, runtime. This gives you the best trial, so it tells you if it had to do self-correcting, in which case, in many cases, it did not. But it tells you also which iteration we actually used in terms of the power. Sometimes we had to go into the last iteration. And then the average pipeline time. So this is not all of them. This is only about half of them, but just to give you a sample of what we have. And just to go a little bit more, so here, this is a good case where we had significant reduction in both power and time. Here's a case where it was after the first trial. This is where we actually found the best energy efficient code refactoring. So, and here's a case where the best candidate for the MI100 was found much earlier than the A100. So it gives us an idea that we're using different refactoring schedules that are based upon the target architecture. And just to give a little bit more too about different optimization strategies. So we classified our optimization strategies into 4 areas, one being memory hierarchy optimization, another one being algorithmic and computational efficiency. So this is where we can look at loop unrolling. We can also look at branch hoisting and things like that, of taking a branch outside of a loop. So we also did parallelism and thread management, where it may have combined threads or group threads, especially in terms of memory sharing. And then some device-specific tuning. And that may be if we can use lower precision, depending upon what we're doing, but what were specific aspects about that architecture. And it was interesting to see, so you can see it was a nice distribution. It wasn't where one area for optimization dominated. So you needed a combination of areas. And then it was very interesting to see with the two different GPUs, that they had similar distributions among the different benchmarks. And so that is the top for both was actually the memory hierarchy optimization. And the one that was used the least per se, and that was parallelism and thread management. So it's very interesting to see that. So just in terms of the results, and that is, and let me just provide a little more clarification here. So with our runs, where we would take a benchmark and go through that pipeline, and we may iterate up to, including the first iteration, maybe 11 total. We ran that, each one reran 30 times, okay? So each of those pipelines for each benchmark, okay? And the reason for doing that is we recognize, for example, the refactoring schedule that you get from large language models is not deterministic. You have some randomness in there, especially dependent upon the temperature that you set with the large language model. And so that was the reason for running it 30 times, okay? Because we wanted to get really good data. And what we found on average, that the energy savings was about 36% for AMD, about 34% for NVIDIA. And it was very similar in terms of the biggest reduction was in the runtime, but you also had reduction in the power. And then I just want to go over one last thing, and I only have 2 slides on this, just so you know. So you don't think I have another 15. Okay, so this is just 2 slides. So I'll finish it in 45 minutes. Total time for the talk. But here, what we looked at was, given we had all these experiments, we wanted to know, because you have some randomness, what's the likeliness of finding the best energy efficiency after, let's say, K is equal to 1. So that's 1 code candidates where you're going through the pipeline. After maybe you have to do 3. Was 30 too many? You know, so what we did was to look at using a Monte Carlo sampling to actually give us expected values for, let's say, a code candidate passing, in terms of that, where K is our number of runs. So if we're doing 1 up to 30, and then we're looking at C as the codes that pass, in terms of passing, where it can go through compilation and execution. And so that's where we have a pass at K, just to tell us, because we do have some randomness in the schedule that's generated, you know, do we need 30 runs? Can we get by with fewer runs? So we did a pass at K measurement or metric. We also, and that's where you're looking at, for example, N choose K, or looking at combinatorics. And here we're doing an energy reduction at K, and that's telling us, are we able to get an energy reduction? And what we really want, and that energy reduction, the middle line is just valid, meaning that it resulted in a lower energy than what we started. And what we look at in terms of that parameter is an energy reduction at K that combines both the pass at K and a valid energy reduction. So how many experiments do we need to do? We did 30, but we wanted to do some sampling to get an expected value of what happens if we do 1, 3, 5 experiments just to see. And what we found is that, for example, the pass rate, when we have K is equal to 1, where we're doing that one lassie, where you're going through 10 iterations, we see the pass rate is around 81%. When we go K equals 3, it goes up to 97%. And if we go K is equal to 5, it's 99. So we could probably get by with K equals 3. Okay. Then when we looked at, and this goes back both devices, AMD and NVIDIA. So when we look at the expected energy reduction, how much better do we get with different number of code candidates that are generated? When we have K equals 1, it's around 29%. When we go to K is equal to 3, that was the interesting part, it was 48%. Then when we get to K is equal to 5, we're around 54 or 54.6%. So it tells us that we don't have to do the 30. We did the 30 so we could do the experiment to see, but we could probably do maybe 3 experiments to get to some good results, because you do have that randomness in terms of the refactoring schedule that's generated. Okay. So wrapping up, so in terms of some of the insights, it's important to have the context with the large language model, to have it also be iterative, and to be self-prompting with the refactoring. Also, you need, well, we actually found there's a large number of optimization strategies that depends upon the code and the target architecture. So we didn't limit any optimization strategies, which we found was really good. We recognized, too, that while we looked at functionality and we did a number of tests with respect to the agent that was the judge to say, is this refactored code same functionality as the original code, we recognize that more work is needed, because when we had some outliers, it was a human in the loop. Okay? So we did check on these things. Then here, it's really good that large language models can be used, especially reasoning models, when you're using cross-language, cross-architecture extensions. And then here, it was really good, the data. So we've archived the data that can be used also in terms of post-tuning of models. So having that data and the metadata available, we're looking at it in terms of doing some post-tuning of models. So it was really interesting. Then just want to mention there are a number of different methods that are looking at energy efficiency. Some of them are, quite a few are static, or looking at it, and that's with like copper. Some of them use like a performance model to actually help guide and say a performance estimate, and we just didn't feel comfortable doing estimates. But it's a lot of work that's too, where people are starting to look at the performance of the codes a lot more, which is good to see. So it's not just having the code that's generated, but you want to have performant code. So with that, I just want to wrap up at the end by saying thanks to Chameleon for enabling this work, because that bare metal platform where we could download the drivers that were needed to do the measurements enabled this work. Without it, we would still be asking if we could get access. We were able to get the time we needed, and that is to do all the experiments that were needed. And then it also provided dedicated access, as you can see. So I'm wrapping up with what I started, but now having seen it, that we really did need to have some dedicated access so we know about our energy measurements. And ending with where I started, with acknowledgements. So that, I'll say thank you.
Thank you very much for a fabulous talk. Any questions for the speaker?
Okay.
You go first.
One of the things that there's been somewhat arguments about is how much does optimizing for energy efficiency differ from just optimizing for performance? And I'm mostly in the camp of if you optimize for performance, you've optimized for energy. So how do you think this work would differ if you were planning to optimize for performance rather than energy?
Would differ, and I can go back and show you. In the table, there's, I think, one entropy where it was a reduction in power, but not a reduction in execution time. Okay, and that's because of the use of a particular resource that you have. So your resources, the issue that comes up with power is that you have different distributions of power usage by different resources within a GPU and a core and CPU. So depending upon how you use them, that can determine your power. It can also determine your execution time, but it's not always the case that it's execution time, because you can use a different resource that's less power, but you didn't pin it to that memory subsystem. And that's what we found, that when we did the pinning, it actually resulted in a lot less power, but it was the same execution time.
Okay, as long as it's the same execution time, you win for sure. That's why I was curious, because if the execution time ends up going up, the idle time on the machine will dominate any optimization for energy. That's why I was curious, yeah.
Right. Mm-hmm. And then sometimes and what we're seeing is you can do both.
Yeah.
And that's the part you want to do. So, but to do both, you need to understand the power distribution among your resources and how to best use them. Yes.
Do you have estimation of the token cost for example, refactoring 1,000 lines of code?
The total cost?
I mean, the token cost.
Oh, the token cost. Oh, we tried not to. It's and I'm just trying to think, was it 1 million tokens? I have to get you the exact number, because we took out token cost from this, because we were using, for example, the large language models that are available at Argonne, and so we weren't paying for them. Argonne was paying for them, and I know Argonne's budget went up. And we took out the token part and said, let's focus on the energy efficiency part, and so I can get you the exact numbers, because we do have it, but we just, yeah. I'll have to go back and see. Okay, because it's just 1,000 lines of code, so it would be those two applications. So I have to go back and see that. But I'll let you know by tomorrow.
Sure.
A couple of questions here.
Yeah, thanks for the talk. I know it wasn't your focus, but I'm wondering if you could offer any subjective thoughts on the quality of the code that's generated, so the readability, maintainability, extensibility.
Okay, and here's the part. Because we started with code that was readable from a benchmark suite, it's not we understood the code that resulted. And I'm just, we didn't necessarily have, what was it? Comments in the code. I guess we understood the code, but maybe it was because we had looked at the code, original code. So it's hard for me to say that, let's say if someone who had not looked at the benchmark codes, looked at the two codes and go, yeah, this is the same level of readability exists. So I think we're a little biased because we knew it was refactoring, so we were looking for the differences. But yeah.
Thank you.
But that's a good question. I'll go back and, and ask that question. And maybe, it makes me think about this. Maybe we'll take our refactored code with people who have never seen the benchmark code and just to ask that question and see what they say, but do a sample. Okay. Yeah.
I have a question actually about the power measurement itself.
Yeah.
So because you're using the NVIDIA and the AMD drivers, you're getting the power that those driver stacks measure. Is there a risk of this optimization just moving power usage from the thing you measure to something you're not measuring? I'm thinking particularly for like the multi-node case, if somehow something gets, say, more network heavy or starts offloading more work onto something that's not part of what you're capturing.
So here, in terms of and that's a good question. Our experiments, we focused on a single node. So we didn't have to worry about the network measurement. So that takes that part out of the loop. But here, and because we were focused on a single node, we felt pretty comfortable with the measurements by the vendor drivers than things that were external to the node. So that was the part. That's a good question.
I think my follow-up to this is, because I work on kind of providing this kind of information, is there some, end-to-end measurement that we could provide, or what would be helpful to help answer this question in the more general case?
Oh, okay. Let's talk a lot more, because yes, having the vendor specific was really good with a single node, and it gave you a lot of measurements across the different components. But when you go external, that is an issue, because now the vendor, it's often a different vendor for the network. And then, you need to have the measurement on the NIC and things like that, and that's not captured. The NIC is not captured. So, yes.
Yeah.
You want to capture that. That would be really good to, yes. Yes, and what is your name?
I'm Mike Sherman.
Mike Sherman, okay. All right. So Mike will be in contact. That would be really good.
There's one more question over there.
Yeah, so I'm convinced that LLMs have the ability to optimize code. I'm trying to understand, or I'm curious to know what's next. Where do you see this going? So I know that Meta has something similar called kernel evolve, where they evolve Triton kernels. But I also know that they are not currently using it for whatever reasons. So what roadblocks do you see in this being adopted, or do you think it's ready for production systems?
So I think a couple of things, and I think the question that you have is being able to, so this one we did, where we worked with a given benchmark suite. We also worked with, single nodes. And a question that comes up is, if you want to go where you're just going from a description of what you want to now energy efficient code, now I think there are some companies that are working on that, but some of the roadblocks, like there's this company I was just looking at, Blitzy. I don't know if you've heard of that. Okay, and it's looking at, what it does is you have to give it a very detailed spec for what you want. So it's not where provide a solver to do this. No, you have to give it a detailed spec, because then it's taking that and its agents are taking and going into modules. And then each agent works on a module and there's a lot of orchestration. So some of the things that I think are important will be, for example, being able to do end-to-end performance and power measurements. You also probably want to do like memory footprint. So you want to do detailed performance measurements, not just timing, but doing detailed performance measurements and having that information feed back. So you have self-improving models that's using that information to feed back and self-improve. But I think we'll get there in some time, but there are these roadblocks of the measurement, being able to conduct the measurement, and also specify correctness, reproducibility, maintainability. Yeah. So it's plenty of research to be done. So, yes.
Very interesting. One thing that I've noticed within like the HPC community is that sometimes there's a cultural resistance to worrying too much about energy efficiency. You have to think about node hours or core hours depending on the machine that you're operating on. So that's always a bit odd for me because I work a lot with edge devices where energy efficiency is very crucial. So I'm just kind of curious, have you thought about trying to port some of this work into for systems that are more edge computing based, where you have like a very strict energy constraint because maybe you're operating a device that has a fixed battery that's attached to it and it only has so much charge to go before it powers out?
So we have started discussions about it. And so, and that's where we were looking at Chameleon with the Edge platform. So we just started looking at it because it is a case where energy and power becomes really important because of your budgets that you have with the devices. But I think HPC is coming around about energy efficiency because you have, exascale machines that require, 40, 50 megawatts. You have data centers. The data centers are exceeding expectations. So you have a lot now where a lot of discussions on energy efficiency, but I think the edge computing would be something good to explore, and we would be happy to work with you.
Awesome.
Okay. Okay.
Okay, thank you again.
Thank you.